We're going to look at a reaction today between an acid and a base. The macroscopic levels what we're going to look at first. Our base is going to be baking soda. The chemical name is sodium hydrogen carbonate. And we're going to add the baking soda. We're going to go ahead and put a little bit of water in here to dissolve the baking soda. Put it into solution. Okay. Use our stirring rod. Okay. So that's our baking soda solution. To that, we're going to add some hydrochloric acid. So I'm going to place this here. So when we add this, you can observe. What you see there is a good bit of bubbles, indicating that a gas is formed and a chemical reaction has occurred. Now we're going to do the same exact reaction, except we're going to look at it in terms of how the pH is changing. To observe our pH changes, we're going to use some universal indicator. So I'm going to do the same thing. A little bit of baking soda. Add a little bit of water. Put it in solution. Stir it up. And we're going to add our indicator. A couple drops. Stir it up. With the universal indicator in, the baking soda is a dark green color, indicating that it has a pH of around 8, which is basic. Okay, and we're going to do the same thing with our hydrochloric acid. So add a little bit of hydrochloric acid. Okay, add some universal indicator, and we get a nice bright red color this time, indicating that we have a pH of around 4 for our universal indicator. Okay. So what happens when an acid and a base mix? You should get a neutralization reaction. Let's see. Just where you can see it. Just add this in. So we should see the nice bubbling occurring again. And a definite color change. You see lots of stuff going on here. Lots of different colors. And we'll need to mix them up. It eventually gets to a kind of a light green color, which indicates that we've just about neutralized it. And it's actually a little beyond neutralization. We added a little bit too much acid, and so we went a little over the neutralization, went a little more acidic. But you can definitely see a color change in our indicator, which shows that we've had a change in pH, which is another more evidence that a chemical reaction has occurred. Now you could do this reaction just as easily with baking soda and vinegar and get the same results. And in fact, it's a little bit easier to get a good neutralization and get this to a good light green color. Okay. So now we're going to take a look at the symbolic version of the reaction that we just saw. It's a lot more complicated than the magnesium-oxygen reaction, as you can see. In the top circle, we have a hydrochloric acid solution. It's an aqueous solution. And so you see a lot of this red with the two whites, that's water. And so aqueous solution, there's lots and lots and lots of water present. And so we're showing that here. When hydrochloric acid dissolves, it breaks into its two ions or dissociates into its two ions. So you can see this small white plus sign here represents your H+. The green with the negative represents your chloride. Interestingly enough, and we'll talk about this in later videos, water is going to orient itself around these ions because of water's polarity. So if you see here the hydrogen part of water, which will be the positive dipole of water, kind of orients around this negative ion because of the positive-negative attraction there. And if you don't know how well this shows it, but yeah, here. So you can have the positive ion here, and you see the negative oxygen part of water is orienting around it. This is called hydration. So it's kind of neat. We'll talk more about polarity and structure in later videos. This bottom circle shows our baking soda or sodium hydrogen carbonate solution. And so again, you've got lots of water molecules. This big yellow positive represents our sodium ion, because again, this is a salt, it dissociates when it dissolves. And this little thing here represents our hydrogen carbonate ion. Alright, so when these two mix, you see, we get two separate products here. And so here we're showing our gas, you can see because the molecules are spaced out, and that represents our gas, and this is CO2, that's the gas that's forming. And in this picture here, you see what's left over in your solution. And in your solution, you have your sodium ions. Notice that the sodium ions didn't change. They didn't change from beginning to end. You have your chloride ions, which did not change from beginning to end. And you have your water. So really, if we look at this reaction in terms of what actually changed, we have a change in our carbon and oxygen to form this gas. And so we'll look at this symbolic version of this reaction. We're going to look at the total reaction, and we're going to look at the net ionic, so we can kind of show you some of these things that we're not changing. We're actually going to leave them out of the reaction. Okay, now we're going to look at the symbolic version of this reaction. So we've got the baking soda, sodium hydrogen carbonate. It's aqueous because a solution with water. Hydrochloric acid, aqueous, also a solution. React to form, we see our carbon dioxide gas, plus sodium chloride, which is aqueous, plus water, liquid. And so this is our overall balanced equation, and it is balanced. We can look at that real quick. So one sodium, one hydrogen plus another hydrogen, that's two hydrogens. You can see here we also have two hydrogens, that's balanced. One carbon. We have three oxygens here. We have two oxygens here plus one in the water, that makes three, so that's balanced. And then one chlorine. So our reaction's balanced. And this is our overall reaction. Now we're going to look at the complete ionic, which means anything that's aqueous, we're going to go ahead and dissociate like we saw in the particulate level picture. When this dissolves, it breaks into two ions, the positive sodium and the negative hydrogen carbonate. Same deal here. So what I'm going to do is just write that. So our baking soda is Na plus, plus HCO3 minus. And that's still aqueous, I just don't have room to write that. CO2 gas, we're not going to break that up because it's not ionic, and it's a gas, so it's kind of coming out, and we're not going to dissociate that. But sodium chloride is a salt, it's ionic, it's definitely soluble, we know this. And then water, liquid, is a pure substance, so we don't dissociate that either. And so this winds up being what we call our complete ionic equation. And so solution, ionic, dissociates into ions. Solution, ionic, dissociates into the ions. Gas does not dissociate, it's a pure substance. Solution, ionic, dissociates, and then water, pure liquid, does not dissociate. Although water does dissociate a little bit, but that's not important for this reaction. Okay, so now what we're going to do is we're going to write our final reaction, which is the net ionic. If you remember back to the particulate level picture, those yellow ions never changed. They were big yellow positive ions at the beginning, big yellow positive ions at the end. And so what we're going to do to write our net ionic is we're going to cross out all ions that are the same on both sides. Because if you think about a chemical reaction, nothing changed there. Sodium plus, no difference. And if you look closely, you see another ion that doesn't change, and that's the chloride ion. That was the green negatively charged ion that remained the same in the particulate level picture. So we cross that out. And so what actually winds up changing is our net ionic, so we'll rewrite that. So hydrogen carbonate ion reacts with H plus to form CO2 plus water. And this is your net ionic. And you can see here, this is balanced still. Okay, we have two hydrogens, one carbon, three oxygens, and three oxygens. It's also balanced in terms of charge, positive, negative here. So your total net charge is 0. If you look over here, your total net charge is also 0. And so this is our base, and this is our acid. The acid actually donates to the base to form carbonic acid, and carbonic acid decomposes rapidly into CO2 and water. And so there's your net ionic equation for what occurs.